In Part 2 of Lecture 3, we will look at designing the symbol table for a particular language. The language that will be the source language of a prototypical compiler will be the JSON programming language. It is a very small language that is not very useful for real programs, but it contains every important language feature that we would want to illustrate while designing a compiler. It is a block-oriented language like Pascal and the C-based languages, including C++ and Java, but it does not use braces to begin or end a block of code. It uses words such as begin, then, else, and do to mark the beginning of a block, and words such as end if, end while, and end until to end a block. JSON has two data types, integers and reals, and it has procedures that pass values by reference. So procedures can pass back values to the procedure or main program that called it. The language is case insensitive, so capital letters are converted to their lowercase equivalents. A JSON program begins with a program header that contains the reserved word program, an identifier that serves as the program's name, and a semicolon. Variables belonging to the main program are then declared after the header, and then we can have the procedures that the programmer wishes to write. After the reserved word procedure and the procedure name, we have the list of formal parameters, each of which has its type preceding it. Even if they all are of the same type, each one must be separately declared with its type directly before the parameter. We can then declare variables local to the procedure, and its code is enclosed between the reserved words begin and end. It should be noted that we can have comments in here as well, beginning with an open brace and ending with a closed brace. The main program appears after procedures are declared, and its code is also enclosed between begin and end. We can see that every statement begins with a reserved word. The read and write statements have the name of the one variable whose value is to be read from input or written as output. The call statement calls the procedure. The set statement assigns a variable with the value of the expression to the right of the equal sign. Since all the operators are single characters, greater than or equal to and less than or equal to are not included in the language. Having both while and until statements precludes the need for these two operators. Since the semicolons are there to separate statements and not to end them, you won't see semicolons before end, else, and the other words ending a block of code. This slide shows all of the tokens in the JSON language, which consists of the token's name preceded by the letters T, O, K. The compiler gives these numeric values starting with 0 for tok begin, 1 for tok call, and so on. We have the semantic types and data types in the language. The semantic types tell us whether a symbol in the program is a reserved word, or a program, a variable, a constant, and so on. We have the data types real and integer, but also program and procedure, so we can determine if the programmer is trying to use this as a value, which would be invalid. Similarly, we can determine if the data type is not yet known, or if there isn't a data type, which would be the case if the symbol is a reserved word or an operator. There are three pieces of information that we store in the name table. Where in the string does the name in question begin? The index of the attribute table's entry for it, and the index for the next name table entry sharing its hash value. We don't need to save the name's length, because each name is terminated with a null byte, in other words, a byte set equal to 0. This makes it easy to spot it. The attribute table is where most of the information is stored. This will include the semantic type, the token, the data type, and the index of the name table entry. If the symbol is a literal, we will store its value here. We obviously expect to see these here, but this will also include the index of the entry for the procedure to which this symbol belongs. We will store a string that will serve as a label for this symbol when it's necessary. We also store the index of the entries for other uses of this identifier in earlier scopes and other identifiers within this scope. We will look at these in more detail later in this lecture. We are now looking at the declaration for the class symbol table, where we will declare the properties and methods of the symbol table. The most natural place to start is with the constructor, which will initialize the various structures in the table, and the method dump, which will print out all the various values stored in the symbol table. While this is not necessary when the compiler is complete, it is extremely useful while we are still testing and debugging it. Install name returns true if the lexeme is already in the symbol table, and if it isn't, it will install it and return false. Is present returns true if the lexeme is in the symbol table and false if it isn't. Install name is one of a few methods that make use of is present. Install attrib creates entries in the attribute table. Set attrib sets the semantic type and data type for a given entry. Install data type installs just the data type for a given entry. Open scope will open the new scope for a specified identifier. Close scope closes an entire scope when we have finished scanning the procedure in question. It is important to keep in mind that we will open a scope one identifier at a time, but we close the entire scope at once. Set proc sets this new procedure as the procedure that we are scanning. It is important because this will also indicate that we may need to open a new scope for identifiers declared here. getProc will return the attribute table index for the current procedure. There are two methods called setValue. They differ in the data type of the value that they are setting. The first one sets a value as float, and the second sets it as integer. Since the parameter lists are different, the compiler will choose the correct version. However, that does not work as well for returning the value. For that reason, we have two separate methods for this purpose. getRValue will return the value if it's real, and getIValue will return the value if it's an integer. getLabel will return the string indicating the address of the variable. The JSON compiler translates the program into Intel assembler, so the label is this compiler's equivalent of a low-level address. Label scope will indicate in which method does this label appear. ParamLabel sets up a label for the procedure's parameters. PrintLexeme and PrintToken will print the lexeme and token respectively. This is very useful when we are debugging. We have three accessors next. getTokeClass returns the token, getDataType returns the data type, and get SM class return the semantic type. The last two are examples of inline functions, meaning that the procedure's code is actually written into the object code where the method is called. While it uses a bit more space than if we actually had only a procedure call here, it runs more quickly. We use this for the next two procedures as well. IsValidType returns true if the identifier belongs to a float or integer type, and table size returns the allocated size of the attribute table. Here we have the private methods as well as our data. Init proc entry initializes the entry that we create for the current symbol on the procedure stack. Hashcode calculates the hash value for the current lexeme. Lexeme in caps prints the lexeme name in uppercase characters. MakeLabel creates a label for our object code in assembly language. Min returns the smaller of two values. This was necessary for the compiler used originally to compile this. We also see definitions for our tables. The string table, again just a very long string, the name table, the attribute table, the hash table, and their respective lengths. We also define the items that are pushed on the procedure stack and the procedure stack itself. Before we can start scanning the program, we must initialize the symbol table. Initialization involves installing all of the reserved words, standard identifiers, and operators. In production compilers, this would not be necessary, since the symbol table would already have been completed with all of this pre-installed before it was released. The first thing that we will do in initializing the symbol table is to set this proc to -1, indicating that it does not correspond to anything in the symbol table yet. When we read the name of the program, this will change. We will now set every entry in the hash table to -1, indicating that it is not pointing to any entries in the name table. Similarly, we will do this for the next name field in the name table, because there are no lists of values sharing a hash value yet. We will now zero out every field in the entire attribute table. The semantic types and tokens are all set to unknown. The pointer back to the name table is -1, indicating that it is not pointing to anything. We set the tag field for the value to integer and its value to 0. This will be changed each time we install a literal in the symbol table. The pointers to owning procedure for variables, the scope pointers are all pointing nowhere, and the label is marked as blank by its beginning byte set to null. Next, we use install name and set attrib to install the reserved words in the symbol table. After the reserved words are all installed, we install the operators. Lastly, we install the only function in the language, float, which converts integers to reals in expressions where both data types are present.